The theory of engineering tensors presented in the previous video required that all bases for the underlying vector space be orthogonal. Now we will extend the theory to allow for non-orthogonal bases. As before, we start with a vector space V, and as before, vectors in V are rank 1 tensors. And now every tensor will have a type classification, and a vector is a type V for vector tensor. The set of linear maps from V to the real numbers is also a vector space, called the dual space or covector space of V, and we will denote this vector space by V star. An element of V star, i.e. a covector, is also a rank 1 tensor, and its type classification is C for covector. Given a set of basis vectors, E1, E2, En for V, for each basis vector EI, we can define a linear map from V to R, denoted by EI star, defined as follows. EI star of EI equals 1, and EI star of EJ equals 0 for j not equal to I. Thus, EI star of EJ equals the Kronecker delta of I and j, which equals 1 if I equals j and 0 otherwise. Then the covectors EI star, E2 star, En star form a basis for the covector space V star. So we can write any covector A star as shown in line 1 as a linear sum of the basis covectors, and it can be written in component form also shown in line 1. If we have a vector B in V and a basis covector EI star maps B to its ith coordinate B sub I as shown in line 3, and A star of B is shown in line 4. We can form tensor products as before using the tensor product operation. On line 1 we have a product of 4 basis tensors, E1 star times EJ times EK star times E1, and that is a rank 4 type CBCB tensor. With V equal to R2, with basis vectors E1 and E2, the tensor products E1 times E1 star, E1 times E2 star, E2 times E1 star, and E2 times E2 star form the basis for a new vector space, a rank 2 tensor product space of type VC. There are 4 types of rank 2 tensors and tensor product spaces as shown in the table. The table shows the basis tensors for 4 types of rank 2 tensors. The types are VB, VC, CV, and CC. As before, a tensor is an element of a tensor product space. For example, a rank 3 type CVC tensor is an element of the tensor product space V star cross V cross V star. Suppose V is R2 with the usual Cartesian basis E1 and E2, and A is a rank 2 type VC tensor with components A, I, J as shown. And now suppose we want to change the basis for V from E1 and E2 to another basis, F1 and F2. In the previous video on engineering tensors, we were restricted to orthonormal bases only. And now we want to remove that restriction, and the F basis is not required to be orthonormal. The old and new basis vectors are shown in the diagram. We can write the vectors F1 and F2 in E-component form as shown on lines 1 and 2. So F1 equals R11 times E1 plus R12 times E2, and F2 equals R21 times E1 plus R22 times E2. R is the direct transformation matrix mapping the E basis vectors to the F basis vectors. With Q equal to R inverse, Q is the direct transformation matrix mapping the F basis vectors to the E basis vectors as shown on lines 3 and 4. Note that E1 star and E2 star are basis vectors for V star, and F1 star and F2 star are also basis vectors for V star. So what is the direct transformation matrix from the E star basis of V star to the F star basis? Let's see. Line 1 shows the E basis vectors as sums of F basis vectors from the previous slide. In line 2, we have the direct transformation from the E star basis to the F star basis, and at this point the coefficients A, B, C, and D are to be determined. Looking at line 3A, F1 star of E1 equals F1 star of Q11 times F1 plus Q12 times F2, and that equals Q11. And F1 star of E1 also equals A times E1 star of E1 plus B times E2 star of E1, and that equals A. So we have that A equals Q11. Similarly, we see that B equals Q21, C equals Q12, and D equals Q22. So we can write the F star basis in E star basis component form, as shown in line 4, and we have that Q transpose is a direct transformation matrix from the E star basis to the F star basis. Thus, Q transpose inverse is the direct transformation matrix from the F star basis to the E star basis. And since the inverse of the transpose of any matrix equals the transpose of the inverse, Q transpose inverse equals Q inverse transpose equals R transpose. So R transpose is the direct transformation matrix from the F star basis to the E star basis. R maps E basis vectors to F basis vectors. Q equals R inverse maps F basis vectors to E basis vectors. Q transpose maps E star basis vectors to F star basis vectors. Q transpose inverse, which equals R transpose, maps F star basis vectors to E star basis vectors. Note that the direct transformation matrices map basis vectors to basis vectors and basis covectors to basis covectors. They do not map vector or covector components. The direct transformation matrices are summarized in a table for your convenience and mine. First, we derive the component transformation rule for a rank 2 type BC tensor A. On line 1, first write A as a sum of B cross B star basis tensors and use the direct transformation matrix for vectors. That is R, to write each E basis vector as a linear combination of F basis vectors, and use the direct transformation rule for B star to write each E star basis vector as a linear sum of F star basis vectors. Line 2, change the order of summation to sum on the I and J indices first, then factor out the F basis tensors. Line 3, read the coefficient of each F basis tensor from line 2. This argument is repeated on the bottom half of the page for rank R tensors. Each E basis vector is replaced by a linear combination of F basis vectors, and each E star basis vector is replaced by a linear combination of F star basis vectors. The order of summation is changed, the F basis tensors are factored out, and we're left with the components of the F basis tensor. Note that if both bases are orthogonal, then R is a rotation matrix, and so R inverse equals R transpose, and hence on line 2 we see that Q transpose equals R inverse transpose equals R transpose transpose, which equals R. So R is also the direct transformation matrix for the basis covectors as well as the basis vectors. Thus both lines in the table of direct transformation matrices are the same. The comeuppance is that when R is a rotation matrix, the component transformation rules are the same for vectors and covectors. And that is why we don't need to distinguish between vectors and covectors when using tensors in engineering applications which only have orthogonal bases for vector spaces. The tensor operations are addition, subtraction, multiplication, and contraction. The formulas are the same as those for engineering tensors covered in the previous video, with one restriction on contraction. And that is, a tensor can be contracted on two indices I and j if and only if one index is a vector index and the other is a covector index. Otherwise, the contraction formula is the same as shown in lines 1 and 2. Probably the first tensor to come into existence was the metric tensor, invented by Gauss in his study of maps and curved space. First, we'll look at the metric tensor in Euclidean space, that is R2. The metric tensor computes the dot product of two vectors, thus the length of any vector v can be computed as the square root of its dot product, or m of v comma v. When the basis for R2 is the usual Cartesian basis, the metric tensor is a rank 2 type CC tensor, the identity matrix in component form. We will calculate the f-basis components of the metric tensor for an example with an oblique f-basis and check that the components are correct. Line 1 shows the direct transformation matrix mapping the e-basis vectors to the f-basis vectors. Line 3 shows the calculation of the f-basis components corresponding to the 2, 3 vector and e-basis components. The f-basis components are -1 and 4.24. Line 1 shows the metric tensor and e-basis components applied to the 2, 3 vector and e-basis components. The result is 13. Line 2 shows the calculation of the metric tensor and f-basis components. Note that since the metric tensor is a rank 2 type CC tensor, R transpose is used to transform the coordinates from the e-basis to the f-basis. Line 3 shows the results of applying the metric tensor and f-basis components to the -1, 4.24 vector and f-basis components, and the result is 13, which is what we were hoping for. The sphere gives us a relatively simple example of a curved two-dimensional surface or space. The lines of latitude and longitude on a sphere define a coordinate system, and we can parameterize all the lines of latitude and longitude simultaneously with the S function shown in line 1. The latitude lines are lines of constant theta, and the longitude lines are lines of constant phi. These lines are curved lines in three-dimensional space. The tangent plane to the sphere at S of theta, phi is spanned by the tangent vectors to the latitude and longitude lines going through the point. Denoting the tangent to the latitude line by E theta and the tangent to the longitude line by E phi, we can calculate values for these vectors by evaluating the expressions shown in lines 2 and 3. The expressions for E theta and E phi are evaluated on lines 1 and 2. We can then evaluate the dot products of E theta and E phi as indicated in line 3. And in line 4, we have the results, the metric tensor for the surface at the point S of theta, phi. Note that the vectors are orthogonal but not orthonormal. The metric tensor is the linchpin in the study of curved spaces as it determines everything about the geometry of the space. And in Gauss's theorem egregium, or remarkable theorem, he proves that the metric tensor can be derived from within the space itself. That is, without embedding the space in a higher dimension flat space as we have done. So, for example, the core of special relativity is the innocuous-looking metric tensor for four-dimensional space-time shown. This metric is a consequence of the Lorentz transform, and the resulting space is called Minkowski space or space-time. Space-time in special relativity is not curved, and the metric tensor is constant, but all the very strange mysteries of special relativity are the result of this metric tensor. The metric tensor in general relativity is determined by a set of very complicated nonlinear differential equations known as the Einstein field equations, relating the geometry of the space represented by the Ricci curvature tensor, the curvature scalar, and the metric tensor to the stress energy tensor. The equations are differential equations because the components of the Ricci curvature tensor contain derivatives of the metric tensor components.
Cool runnings, take my hand. Cool runnings, no regret about it. I got the situation well in hand. I know what time to see gets stormy, and pestilence to come upon the land. Trials and tribulations